Firstly, I think we should thank the organizers because they're amazing guys, both in personality and in physics. And they put together an amazing group of people, everyone here and the people that have left. But also I think we should thank you guys because you guys are an amazing group of people. And you know, they say when someone gives a good talk, you want to change your field. And now I feel like I want to start in 20 new different fields after this conference. But also, we'd like to stay in contact with all of you guys because it was very interesting, the discussions we had, and both about physics and not about physics. The title of the talk is Distinct Topological Magnetic Textures and Antiskyrmion Hosting Compounds, MnxYZ, with different Berry curvature responses. And so the idea is that we try to look at certain compounds and just by really trying to fight with these materials and this sandbox of materials to really understand what the underlying mechanisms are to stabilize magnetic textures. And with the fact that we want them to be topological. And then from that, you have some texture and you apply some field and you get some response. And this is what we mean by Berry curvature response. Maybe Maz would like to say something like a hyperbolic response, but I am not so good with hyperboles. So there's also the collaborators. So I'm not an island. I like to work very closely with many other people. As you guys know, I'm very social. And so it's not only me, but we work with experimentalists. And so a lot of these guys are PhD students that grew the samples, did neutron measurements, did transport, also did calculations. We worked across different experimental groups and also with other theorists and things like this. We're also funded by a lot of different projects. So there's the Skyrmions project, the SkyTop, which tries to mix topological materials and Skyrmions, which is exactly what this conference does. There's ERC, of course. There's ASPEN, which is also a very big part of this project because the idea is that we don't really want to go to antiferromagnetic, but we want to go to something that's very close to antiferromagnetic, which is a ferromagnetic with nearly compensated spin. And then there's also newly this IMPRS, which we are right now actually looking for PhD students, both in experiment and theory, to actually really trying to tackle these Skyrmion systems in 3D. To continue, Skyrmions, I do not have to talk so much about this because I believe Christina gave a very beautiful introduction with beautiful pictures, and I don't think I could say it any better, but one main thing is, you see this phase diagram of this manganese silicon. It was the first phase diagram for a Skyrmion. It was the first phase diagram where they knew it was a Skyrmion. This A phase has actually existed for about 40 years or so. They just didn't know what was inside it. And this is for manganese silicon. And what's nice about this is that from 2009, which I don't have the year here, but within 10 years, we went from below 30 Kelvin to up to 300 Kelvin for stabilizing Skyrmions. And this is very nice for field of condensed matter physics because, as you know, like superconductivity has existed at a very low temperature for a very long time. What's also nice about this is you can stabilize Skyrmions in the zero magnetic field. This is actually the phase diagram for one of these Heusler compounds, which stabilizes this anti-Skyrmion. And I will explain very quickly what that is in a moment. What's also nice is that you can couple Skyrmions and anti-Skyrmions and magnetic textures to other phases of quantum materials or condensed matter, such as superconductors, and you can also try to connect it to wild materials and use these for devices. And that is the main goal of what we do, is we want to have a material, know everything about it, and be able to make a device that works for humanity. What's also nice is that you can scale these materials just by dimensionality, so you can change the size, change how many appear, and that makes it very nice because you have a very fine-tuned way of controlling these materials. So this is Conor McGregor getting punched in the face. Some people like him here, but what I want to say here is what we do is we try to take a main field approximation, this Kohn-Sham approximation, and we try to map it to this classical equation, yeah? So you have different interactions here. You have something what's called exchange interaction. Usually people think of this as the nearest neighbor interaction or exchange field, but this tells you that, hey, all of my spins in my system want to point in the same way, yeah? Any direction doesn't matter, but they all want to do the same thing, or they want to point oppositely to each other. But this gives the ordering to your sample and also tells you the Curie temperature. The next one is this Delasinski-Moyer interaction, which is very similar to the exchange, but it involves spin-orbit coupling. And this tells people, hey, I want to point orthogonal to you, yeah? So this gives some chiral sense to your system. You have anisotropy, which tells you which direction your spins want to point. You have the magnetic field, which likes to make new magnetic states. You have also this, what's called this dipole-dipole interaction. And you also have these other forms of exchange, which are like 4-spin and 3-spins, which I will not talk about today because I think we need to try to understand the basics first and not do too many things. But the reason why I have this picture here is that when the interactions come together and when they're fighting, when they come into contact with each other, this is how you stabilize non-collinear textures, non-coplanar textures. And one of them is this common triangular lattice where, due to the frustration, this fighting on the lattice, you can stabilize the antiferromagnetic lattice in plane just because all the spins don't want to align ferromagnetically. You can also stabilize non-coplanar textures, which I'll show you exactly how we do this in this system. And of course, you can stabilize skyrmions, and this is when all of these guys come in together. And of course, there's other exchange interactions, but on the basic level, these are the most important. To continue. So what the outline of it will be is mostly about these interactions, with the exception of the B field, because we all know what a B field looks like, and we don't need to really discuss how that comes out. But we will not really talk about skyrmions. We're more interested in antiskyrmions, of course, because these are the hot new skyrmions in the field because they are anisotropic and they're quite stable and they form at room temperature. Then I will tell you about the crystal structure of these materials that we look for antiskyrmions in and what the basic interactions are. I will show you some DFT and predictive results on the strain effects, which are quite interesting and allow for multiple distinct topological states. And then I would talk about how we actually tune this Hamiltonian by fighting with it and twisting and turning and straining by putting chemical substitution in, and what the transport comes out like this, and it actually matches very well with the experiment. And then I will talk lastly about, what we do is we grow thin films with the experiment and how this amount of manganese in your system can really change the interactions and give new results. So yeah, I went that a little faster than I thought, but these are pictures here, so I forgot about it, I'm sorry. So there's the crystal structure, the strain effects, which you can use by adding a piezoelectric to your system and changing the size, transport, and that's mainly it. So one quick note about skyrmions, this is the block skyrmion, which Christina showed earlier, and the nail skyrmion also I think was shown by Paolo. There's an antiskyrmion, and they have specific symmetry. So there are a couple of things about these. Is that one, you have to notice that all three of these cases have, well, not all three, but this one has a different topological charge to the other two, yeah? So these two have, you can say +1, and this one has -1. What's important here is that they all have the same ferromagnetic background. So all of them have spins up on infinity and spins down at the center. And so what you can do is you can actually just turn your field around and you get the opposite charge. But for me, this is not really a change in topology, because if I just turn my head upside down, this will not you cannot change the topology of a system by turning your head upside down. The other thing that happens here is that you get actually two other skyrmions out of the system that are very close in symmetry. It looks very similar to this, but just a bit rotated, and also this one, just a bit rotated. But another thing you get from this is that because of the symmetry relations, when you stabilize the skyrmion by DMI, you can never stabilize two distinct skyrmion classes in the same system, unless you really, really go a priori to engineer a system from the ground up. And one material, it's not really possible to stabilize two types of skyrmions. So the Heusler compound, which is, I think everyone knows about Heuslers. They seem to be the most biggest class of materials, because what happens is when you grow them, they just like to mix. Like they just mix everything in there. Very diverse compounds. One of the more famous ones that was discovered a while ago was this cubic Heusler, or this half metallic that Phoebe talked about yesterday is something like this, platinum manganese tin. And what happens here is you have these red atoms, which are the manganese, the gray, which is the platinum, and the tin, which is the green atoms here. And as you begin to add more manganese, you have a problem here. What happens is you start putting in more densitive states, and you put them in right at the framing energy. And this becomes unstable for the system. And this actually causes what's called a Jahn-Teller distortion. So what happens is the system becomes tetragonal to push all your D states down. And so this is the manganese 2 platinum tin, which is what we'll talk about today. And then what happens is we want to say, okay, let's take a little bit more manganese out. And what happens is you get this superstructure that forms. And this is the structure that was shown for this phase diagram. And some very interesting things happen in actually both of these two compounds, which are very similar. You will see in some slides earlier exactly how this structure fits into here, but this superstructure has something called a spin reorientation transition. So at low temperatures, the spins do not align completely. And as you increase the temperature, there's a reorientation, and they all align either ferrimagnetically or ferromagnetically. And so from this, you get two types of transitions, which was not so easy to understand what the origin is, but we will show what the origin is quite soon, is you get this non-coplanar texture, and you get this Antiskyrmion in finite fields. And this, of course, will lead to one of these Berry curvature responses, which we call the Topological Hall effect. So as you apply a current to this, not a very large current, these electrons get deflected by this magnetic field of the skyrmion, and you get some Topological Hall effect that depends on the temperature because of the spin orientation transition. How do you effectively change this? There's many ways to change this. You can add, you can shift the electron occupation, usually by the tin atom. If you change it to antimony or so, you put more or less electrons in, and that can change all of your parameters, such as your anisotropy, your exchange, your DMI. You technically can change the platinum, and you would think platinum has the largest spin-over coupling. And we'll see very soon that platinum is not the best case, but it really depends on what your electronic structure looks like. So you can really, by orders of magnitude, change your system by changing these atoms by 1 electron or so, or a very small amount in spin-over coupling. And then, of course, the magnetization comes from the manganese atoms. And this all gives rise to this classical Hamiltonian that we were talking about. To continue, what is this Hamiltonian? Yeah, so we will go through this very slowly, and then through the results, we'll go a little quicker. So what is, you have exchange. Exchange is something usually between two atoms that want to connect, collinear or anti-collinear. It's usually on the order of m squared. Then you have this DMI, which is due to some broken inversion symmetry and some spin-orbit coupling that causes a canceling of the spins. You have this anisotropy, which you have many different orders of the anisotropy, but it says, hey, I want to align some direction due to this field. You have this dipole-dipole interaction, and you also have this biquadratic interaction, which we don't discuss so much. But mainly, you want to know that the level of energy of these things, so the exchange interaction is usually about 100 millieV. It can go down to 10 millieV or up to 1,000 millieV, but it's usually the largest interaction in the set. And then comes this DMI, and this can also shift very much, also from 0.1 millieV to 0 to even more. Then you have also this anisotropy, which is a little bit weaker than DMI because it goes something like the spin orbit squared. And then you have this dipole-dipole interaction, which is very weak because it's very long range, and it dies off very quickly. And then you have this biquadratic, which we'll not talk about. The magnetic crystalline anisotropy is actually probably one of the more important things in stabilizing skyrmions. So in the B20 compounds, you usually have anisotropies that look something like this. You have this cubic anisotropy that either has an easy plane or an easy axis. So for iron, it's this easy axis. It likes to go on 0, 0, 1, the 1, 0, 0, and the spins can point in any direction. They're all the same energy. And you can already see how this can help to stabilize magnetic textures, because now you can say, hey, I can point my spins on any of these axes with a low amount of energy. Then you have this nickel case, which is the easy axis is along the 1, 1, 1. So you can see how these have very different things. For the tetragonal cases, in the simplest form, it's much more complicated in these examples, so you have to go to a couple more terms here, but you usually either have an easy axis or an easy plane and a hard axis. And it just depends on the signs of these things. So then there's the dipole-dipole, and dipole-dipole creates non-collinear textures in several different ways. One is this case here, where you have some material and you say, I want my magnetization to be up, and over here I have some magnetization, I want my magnetization to be down. And dipole-dipole, you can see very quickly, there's a minus sign here and there's a dot product, and that already says all these guys want to point in the same direction. But also, because of the way it's written, you have these symmetry terms between the atoms. So if you have more atoms to the left and right of you, then you want to point with those guys in a certain direction compared to pointing to the guys above. And so what it does is it will cause some rotation across this case, and the case where you have infinite in this direction, and here you stop growing your sample, it will start to point in plane and then somehow change its direction. And then in the case when you have a spiral, it will want to push it larger, just to want things to be ferromagnetic. Then there's the exchange, and this is where the interesting strings start to come in. So for one, I said you have this antiferromagnetic lattice, and when the exchange is positive, this third case doesn't know what to do, so it forces everything to be antiferromagnetic. Sorry, that was for if the exchange is antiferromagnetic and each spin wants to point anti-parallel to each other, you have a third site where they will force to be pointing in plane, which is this case. And this is one of the first cases of non-collinear, and this, if you've seen the work of Jakub Železný and others, that this has a very interesting Berry curvature responses in the manganese 310, the manganese 3 iridium, in cases like this. As you look at the Magnon the dispersion of this is just a Q-squared dispersion, so a quadratic equation that Frank likes a lot. And without any D, it's not so interesting, but there's other cases when you start to put in different neighboring interactions of exchange. So there is the first nearest neighbor exchange for these manganese platinum tin compounds, which is shown here. It was the same crystal structure as before. This pink line here is the manganese platinum tin. And then what you have is this first nearest neighbor interaction, which is the green, and then you can put in another case, which is this second nearest neighbor interaction, and the third nearest neighbor interaction. And what this does is it actually creates your non-collinear texture. So this guy always wants to be ferromagnetic or antiferromagnetic. This guy wants to be ferromagnetic, and then this guy wants to be antiferromagnetic. And what this causes is when there's some competition between these two, you can create spin spirals and non-collinear textures. And but it depends on how strong someone fights. And they have to be a little bit better than Conor McGregor to actually start to create these spirals and things like this. The DMI, or let's kind of take shift a bit. So we have this new Hamiltonian now, which is your DFT Hamiltonian. You have your hopping, your spin-over coupling, maybe have some spatial dependence of your magnetization. And you can also have some impurities and things like this, which is, or vacancies or something like this, which changes the potential of your lattice. And what this does is it leads to two effects. One is when you apply electric field, you get this momentum space effect, which is this anomalous Hall effect I think everyone knows about. And then when you have some magnetic texture like a Skyrmion here, you also get this real space barrier curvature, which is this effective magnetic field that also gives you anomalous Hall effect-like behavior. This we usually call the topological Hall effect, but it gets very confusing because there's many things that are called the topological Hall effect that should not probably be called the topological Hall effect. But as we heard from Maz the other day, this creates a hyperbolic field and this causes transport in the transverse direction. So this is just a Skyrmion plotted in a hyperbolic, as a hyperbolic function. The other thing that you can see is that as you mix these two things, the magnetization and the spin-orbit coupling, this is where you get these phase space barrier curvatures. So in momentum space and real space, you get the Antiskyrmion interaction, which is not a transport response, but it's a ground state property. And this comes from this what's called a ground state spin current between the atoms. Yeah? So it's not a real current, but it's just you're exchanging the electrons, and this causes the DMI. This causes spins to point perpendicular, as we said, and create spirals. And what it does to that quadratic equation is just shifts it down. Everyone's cool so far? And now is where things get tricky because I deleted this last part of the biquadratic and constrained magnetism to make things faster, but we will go now to the strain effects of things. If you guys have questions, totally stop me and ask me. Yeah, I have a timer. So yeah, the first compound is the manganese 2-rhodium-10. Here's the band structure, spaghetti plot, not so interesting. What's actually more interesting is the DMI in this system. Now, as we said earlier, the DMI comes from platinum. You know, platinum and these 5D elements have all the spin-orbit coupling. But now as you actually look at this Berry curvature as a function of energy, at the Fermi energy, the DMI is mostly coming from this green case, which is 10, which seems very strange. It's like a p orbital giving you DMI. But it's because these p orbitals do have spin-orbit coupling, but they're also much more extended than the d elements. And as I said, you have this Jahn-Teller distortion, which puts all the d states down. And so, yeah, if you can shift your Fermi energy here, then you can get a larger DMI due to your 5D elements, okay? But yeah, that's the case. So now let's switch a little bit over. Manganese 2-rhodium-10 is actually something very nice because there's a lot of experiments done on it. And so what we did was something not so interesting. We just changed the size of the lattice, yeah? So we put pressure or we put it strain. And what we saw was that this energy dispersion went from having 2 minimum to 1 minimum. And what is the reason for this, yeah? And what you see was exactly that these neighboring exchanges actually changed in their order of who's stronger and who's weaker. This red one is the largest interaction, but it causes everything to be ferromagnetic. The black is the third nearest neighbor interaction, which causes non-coplanar canting. And then we also looked for some other things, such as the spin-orbit effect, such as how non-collinear it is as a function of strain, and what's called the magnetic crystalline anisotropy. We looked, how does the energy change between 2 different directions? And you see the magnetic crystalline anisotropy is actually very weak. When it's positive, it's out of plane. When it's negative, it's in plane. So it's very weakly in plane, but it doesn't change as a function of strain. Do you have a question? Okay, sorry. And then you also have things like the DMI, which does not change also as a function of strain. Then we said, okay, yeah, let's do some LOG equation type things. Simple, not on a quantum level like Christina, but we take this manganese 2-rhodium-10 and we just flatten it down to a simple model with these 3 exchange interactions we have. And when we're above the spin orientation, we get these very nice antiskyrmions that form, they're ferromagnetic. So what's nice about being ferromagnetic is that they are almost like an antiferromagnetic, so they should move closer like antiferromagnetic systems, but they also have a very large spin moment, so you can still detect them in types of things like LTM and other systems. And then we went, what happens below the spin orientation? And we got something very weird here, actually. At first, it looked like a skyrmion, but when you actually look closer, it's actually a little bit more elliptical, and it still looks like a skyrmion. But what happens is you can see it's very asymmetric here on this side and this side, where these two are very symmetric. And what happens here is that it is antiskyrmion, but it's very elliptical. In this case, when you do the numerics of it, you find that you have a charge for an antiskyrmion. Chemical substitution and transport. Here's pretty quickly. I mean, these are a lot of graphs, so don't worry about it. I mean, the main thing is that as you put in more manganese, you go from manganese 1.5 to manganese 2, you really do change how the structure behaves and what the fundamental interactions are. You also can change the magnetization, and you can also change the energetics of these systems, and you change the size of these systems a lot. Another thing we did is we did many more compounds, but we just do a few here. We just, change the Z element, change the X element, the Y element, and we look at the DMI and anomalous Hall effect. So these are somewhat correlated because the anomalous Hall effect is a spin-orbit effect also, but it's the momentum space. The DMI will tell you the size of your skyrmions, which will also tell you the size of your effective transport. And so what you really see is that it really goes up when you put iridium in these cases or you put ruthenium in. So this is just because you shift the Fermi energy down to that point where the Jahn-Teller distortion causes this. As a function of strain, the DMI doesn't change, and you can see you also have DMI on all the lattices, but the strongest is always just close to interactions. Now let me go to some transport. I have 5 minutes. Perfect. To transport, this is actually a real experiment. The student worked very hard to grow single crystals of this material. This is the manganese 1.4 platinum 10. And what he saw was, depending on which direction you apply the field, you get topological, or at that time, what they call topological Hall effect is just you make a Hall measurement and you subtract all your anomalous Hall and your ordinary Hall, which can be actually quite tedious, but the student worked very long on it, and he saw 2 different topological Hall transports, and I said, hey, let's do some analysis on this. And so we did, for the top one, we did the analysis. I showed him how to do this anomalous Hall effect, take out the anomalous Hall effect. So the anomalous Hall effect is very intrinsic. You have this quadratic dependence in the resistivity, and you have some small skew scattering there. And then he also did it for the topological Hall effect part that he subtracted. He got the strong quadratic case, so it's pretty much an anomalous Hall effect. But when he did it for the 001 direction, he saw for anomalous Hall effect, quadratic behavior with a bit stronger skew scattering term. But for the topological Hall effect, he saw this completely flat line. And this is completely due, it's not quantized in terms of the quantum Hall effect, but it is a quanta of charge coming, not charge, but it's a quanta of skyrmions that you have. So it stays flat. So what he does here is he takes the maximum topological Hall effect for any given field at any given temperature. We continue with these compounds and did many other cases, and from these transport dynamics, we can point to, okay, if you have an anti-Skyrmion phase, as you put palladium or rhodium in, or a non-coplanar phase, or a ferromagnetic phase. And this is really just playing with the transport, if it aligns with the magnetization or not. To continue, and then, this is almost to the end. 3 minutes? 4, 5, let's say 5. So then we take the single crystals of the manganese platinum 10, and we fibbed it, and we made devices with different thicknesses. What we saw was some very interesting results. So let's start with the high temperature results. You have a bit of a skyrmion here that shows up as a very small pocket, and this just comes into some hysteresis. So when you apply them as you do a magnetization sweep, for one direction the skyrmion forms, in the other case it doesn't form. So you get a little bit of a hysteresis in your transport. Not in your magnetization, but your transport. And then I said, yeah, okay, now we have to go below this high temperature. This is actually still a little bit below the spin orientation. So you still have some interesting things here. But then we go very much below, about, I think, 1.8 Kelvin. And you still see when you have your magnetic field perpendicular to, or parallel to the sea, you have some hysteresis here, which gives you topological Hall effect. And then what happens is you start to, or if you look through this actually, on the high field case, you have anomalous Hall effect, and ordinary Hall effect, and also planar Hall effect. But then when you get to lower fields, you actually see a couple features. You see this bump, which comes from this non-coplanar part, and then you also see this hysteresis, which is, you get this skyrmion that actually forms from an in-plane field, if everyone follows. Okay? So this here is just the simulations. We take a magnetic field and rotate it in our sample, and we can actually see it. So here is the skyrmion state. Here's this spin spiral state that's non-coplanar, and here's this non-coplanar state, which is just everything's non-coplanar. And one thing you already see actually is that the skyrmion state has, the skyrmion state does not match this exact point, but because it's the higher field case, but one thing you actually see is that the skyrmion state has a much lower topological Hall effect than the non-coplanar texture or the spin spiral texture, which seems to be the case for almost all skyrmion systems. But yeah, we continue. The last part is just this manganese concentration and thickness. So we also grew thin films of this with a similar model we took from the manganese rhodium 10 and the manganese platinum 10, but now we actually, instead of having this 2D plane, we made it 3D because we wanted to look as a function of thickness. we take a sweep of the magnetization of the field, and we see the magnetization has 2 hysteresis loops. This here is the experiment at 50 Kelvin, so you have these 2 hysteresis loops for in and out of plane, and you see you have this extra anisotropy here, and this comes directly from this non-equal planar texture, which wants to force against everything pointing together. So that's where the anisotropy comes from. And then this is at higher temperature where that completely goes away where there's no non-equal planar texture. Topological Hall effect things, so then the student went through and did a lot of work, so he grew this is not even all the work I think he did. He's got like about 10 times more data points. But he grew many different thicknesses and many different concentrations just to see how the anomalous Hall effect and the topological Hall effect behave. And this was the case of thickness, which I tried to reproduce. And so what we saw was that once you add the dipole-dipole term, it actually does curve off because of this anisotropy the dipole-dipole term gives you to the system. I think this is the end. I want to thank you guys all for your attention. This is my son. He's in front of a sandbox, but here is that we have all of these materials and all of these tools, and the sandbox looks quite big, but if you get into it, you're going to have some fun.